Hello, this is Mr. White, and this video is on extrema on an interval, minima and maxima on an interval. And here are the intervals mentioned in that title of the video. And let's get to the first one. So we're going to find any critical numbers of the function f of theta equals 2 secant theta plus tangent theta. And recall that critical numbers are numbers that are in the domain of the function. In other words, you have to be able to plug them into this original equation and get real outputs. So critical numbers are in the domain of the function, and they make the first derivative either equal to 0 or undefined. So our first objective is to find the first derivative, f prime of theta. So we should be at a point now where we're pretty fluent with our trig derivatives, and we know that 2 secant of theta is going to be give us a derivative of 2 secant theta tangent theta, and that the derivative of tangent theta will be secant squared theta. And again, as a critical number, in order to find critical numbers, we will set that first derivative equal to 0. And often students get lazy and just want to put 0, or they just forget. We should be very deliberate and always put 0 or undefined when we're seeking critical numbers. All right. That is not obvious what the solutions are going to be, so let's do a little bit of algebra here. Let's take the greatest common factor out, and that would be secant of theta. That goes into both this term and that term. Inside the big parentheses, we'll put a 2 tangent theta plus secant theta. And again, 0 or undefined. And it's still not totally obvious what to do with this, so let's recall some of our basic trig identities from pre-calc. Let's do that general approach where we turn everything into sines and cosines. So inside the parentheses, that 2 tangent theta will become 2 sine theta over cosine theta. And in a stroke of luck, we notice that that second term, the secant of theta, that's going to be 1 over cosine theta. And without even trying, we've got a common denominator. So let's put plus 1 over that same cosine theta. And as far as the secant theta goes, let's put this as 1 over cosine theta equals 0 or undefined. Feels like we're getting somewhere. Let's do one more little step of simplifying, and we'll have 2 sine of theta plus 1 on the top over cosine times cosine gives us cosine squared theta equals 0 or undefined. All right, so what is going to make this fraction equal to 0? That's going to be when the numerator is equal to 0. What's going to make that fraction be undefined? That's when the denominator is going to be equal to 0. So let's think of this as 2 separate equations where we set the numerator equal to 0 and then the denominator equal to 0 and solve. If we set that numerator equal to 0, 2 sine theta plus 1 equals 0. That's the same as saying sine theta equals negative 1/2. And thinking of our unit circle and also recalling that back at the outset we said we're only working on the interval from 0 to 2 pi. We should know from the unit circle that there are technically infinitely many solutions to this equation, but we only want the ones from 0 to 2 pi. So we'll put theta equals 7 pi over 6 or 11 pi over 6. Now, if we set the denominator equal to 0, that's again what's going to make this derivative undefined. If we set the denominator equal to 0, we get cosine squared equals 0. Cosine squared of theta equals 0. Take the square root of both sides. Cosine theta equals 0. And that only occurs on the interval from 0 to 2 pi at theta equals pi over 2 and 3 pi over 2. So at first glance, it looks like we may have 4 critical numbers. But hold on. Remember what I said at the outset? That critical numbers have to be in the domain of the original function. Notice that pi over 2 and 3 pi over 2 do not give real outputs for the original function. Secant of pi over 2 and 3 pi over 2 is going to be undefined. And in fact, actually tangent of pi over 2 or 3 pi over 2 is also undefined. So all the more reason that we cannot say that those are critical numbers. So these two we won't count. However, that function certainly is defined for these two. So that's what we'll call our critical numbers. And put a box around it, we're done. And just to remind ourselves again, get a sense of what critical numbers do, what they tell us about a function. Let's take a look. We're not asked to do this, but it's not a bad idea to try to get this understanding. If I look at a graph of the function, which you see here twice, notice that at one point, or the left-hand graph, I'm traced to 7 pi over 6, and that happens to be right there. And we can imagine that the derivative is, or that the slope is 0 at that point, right? Likewise, on the right-hand graph, 11 pi over 6 is this point over here. And again, we can imagine that the tangent line does, at least visually, look like it could very well be 0 there. I will also point out that as far as the pi over 2 and the 3 pi over 2, let me point out that that's where we happen to have asymptotes, vertical asymptotes at the graph. So again, the function is undefined there. All right, let's go on to the next one. We are to locate the absolute extrema of the function on the closed interval from 0 to 4. And you notice in the previous exercise that critical numbers tend to give us, or will often give us, minimum and maximum points. So once again, our first objective is to find the derivative here. And being a polynomial, this is going to be pretty quick and straightforward. This first derivative is 3x squared minus 12. And once again, we'll set that equal to 0 or undefined. And this one is a little bit easier than that previous trig problem here. We'll move the 12 over, get 3x squared equals 12, divide by 3, x squared equals 4, and that tells us that x equals -2 or +2. Now, I'm always stressing you guys about remembering to do the plus or minus. However, I will point out in this case, remember, we are asked to work only on this interval from 0 to 4. So if we didn't have that restriction, we'd refer to them both as critical numbers. And we can still refer to -2 as a critical number. However, we're not interested in it here. So this will be our critical number. And remember, in order to look for extrema, we'll look at the critical numbers. And I'll point out right away, real quickly too, perhaps this was obvious, but there's no way that we get any undefined. So again, undefined didn't yield any critical numbers here. Anyway, remember, we have to look for extrema not only at the critical numbers, but at the endpoints of the interval. So this is where our book would typically make a table for left endpoint, any number of critical numbers. And if there are multiple critical numbers to look at, we would have multiple spaces for them. But we only have one that we're interested in here. And then right endpoint. So let me shrink that down a little bit. And let's see what's going on at those 3 locations. At the left endpoint, let's see what's happening at f of 0. That's our left endpoint of the interval. And if I plug 0 into the original equation, 0 cubed minus 12 times 0, that's a pretty easy mental calculation, gives us 0. How about at the critical number? That's going to be f of 2, our critical number there. 2 cubed would be 8. Minus 12 times 2, which is 24, so 8 minus 24 will give us -16. And finally, right endpoint. There's a 4 there. That's our right endpoint, so f of 4 is going to equal, and I guess I really, just as a formality, should be putting it there. Here, 4 cubed is going to be 64, minus 12 times 4, which is 48, so that's going to be +16. So if we think about this graphically, we can imagine that we've got a coordinate plane, and we are only interested in from 0 to 1, 2, 3, 4. And we know that we've got, at f of 0, we've got 0. We know that at f of 2, we've got -16. And we know that at f of 4, we've got a positive 16. And we know that those are the only possible locations where extrema will occur. So we kind of get a sense of what the shape probably looks like. But we don't even really have to fill in the gaps. You don't have to completely understand what it looks like. We know those are where the extrema occur, and we can tell that this is going to be our maximum, our absolute maximum on the interval, and this will be our minimum. So we will put, let's see, our absolute maximum on the interval for this value, and this would be our absolute minimum on the interval. And just because it's so easy to check graphically on the calculator, not a bad idea to do so. If I type the original function into the calculator, I've got these window settings that I'll use. Notice that my y scale is set to 5, so along the y-axis will jump in increments of 5. And if I go to graph, I see that sure enough, if I trace to 2, I get my minimum value, or y equals negative 16. And if I trace to 4, I get that clear maximum point on this interval of positive 16. All right, let's go on to the third one. Here we are asked to use a graphing utility to graph the function and locate the extrema on the closed interval. And I just copied those instructions from the textbook, and I wanted to acknowledge that that's what the textbook asked us to do, and also acknowledge that there are times where we want to be proficient with the graphing calculator, and there are times where it's appropriate to use. But I say let's challenge ourselves to not use the graphing calculator here. We'll back up our results later, but let's acknowledge that this is one we don't need a calculator for. We should be able to draw a piecewise function without a calculator. Notice that for this interval from 1 to 5, that for the first half of that interval, from 1 to 3, we'll use this equation. And for the second half of that interval, 3 to 5, we'll use this other equation. So let's look at this as a transformation. We see a basic parabola that has been flipped across the x-axis and then translated up by 2. Those are all of those pre-calc skills coming into play here. So let's just draw a picture here. And as often, we don't have to be super precise here, or at least I don't think it's necessary. 3, 4, 5. We'll say that's 5. Just as precise as is needed to get the job done. So let's draw our upside down parabola, 2 minus x squared. I should notice that the x-intercept here is going to be square root of 2. So if I were to plug a 1.414 or root 2 in here, that's what would give me my 0. So right around the 1.414 mark, I'll at least try to get that reasonably accurate. I know again that this is a frowny face parabola, so it's going to look something like this. And we're going all the way to 3 on that one, right? So let me do that. And again, I was trying to get all the way to where x equals 3. And let's ask ourselves, what values are we dealing with there? And again, I really should point out too, I'm really only interested on the interval from 1 to 3, between those two lines. But it's an easy reference point to put this, this y-intercept. So when I plug in x equals 0, I get a y equals 2. That's our y-intercept. When I plug in an x equals 1, I get 2 minus 1 squared. This is going to be a 1 here. When I plug in the x equals 3, and why am I plugging in 3? Because it's the endpoint of that subinterval, as I'll call it. And if I do 2 minus 3 squared, that's going to be 2 minus 9. That's going to be negative 7. And since that's x is less than 3, not less than or equal to 3, I'm going to put a little hole there, signifying that that was x less than 3, not less than or equal to 3. So that covers this part of the piecewise function. Let's now shift our attention to this part here. And let's start with this first endpoint. Let's start with that x at 3, x value of 3. If I plug a 3 in here, I get 2 minus 3 times 3. Again, that's 2 minus 9. So it turns out that this picks up right where the last one left off. It picks up with point right there, plugs in the hole. We could tell this is going to be a linear equation with a slope of -3. So I'm going to need to clear myself a little room here. Let's grab that and shrink it down a little bit. All right. And since and let's go ahead and plug in the right endpoint. Let's plug in what happens at x equals 5. 2 minus 3 times 5, that's 2 minus 15. That's -13. So somewhere, let's say right about here, we know we have a line there. If I go over here, that was at -13. And again, given what we've been asked to do, to just find the extrema on the interval, this isn't the prettiest picture in the world, but it's enough to get the job done. We do just simply have to remind ourselves that we're working on the interval from 1 to 5, so let's not fall into the trap of saying that this point is a maximum. That's not on the interval, right? Our interval is from 1 to 5, so we need to work between those two lines, and we just clearly see that the absolute maximum on that interval occurs on the left endpoint, and that's going to be at where x equals 1, and we said y would equal 1 at that value. And we can tell just visually that the lowest point on this stretch of graph is the absolute minimum, and that's going to be at the right endpoint. So the absolute minimum on this interval is going to be where x equals 5 and y equals -13. Easy as that. Again, most of the time when you're given a piecewise function in this class or on the AP exam, it's not going to be a terribly hard one, and I would encourage you to normally just tackle it by hand. I will go ahead and acknowledge the way we were originally asked to do this with the graphing utility, and I've probably shown this in class. I'm not going to go into detail here, but I hope as you see this, you'll go, oh yeah, I kind of remember that. But again, I don't know about you, I look at this and I feel like it's really kind of more work to go into the, enter all this into the graphing calculator. Notice that even though this is one function, I just entered it here on 2 separate lines as if it were 2 separate functions. And as usual, we have to beware, if we were to look at our calculator, we might not be sure just visually whether there's a hole there or not. It's not always clear on our calculator.